We're going to continue on from where we left off yesterday on the microservice ecosystem. So quick recap, we talked about ecosystems in general, service-oriented computing, monolith versus microservice, a couple of case studies, defining your microservices. What's the word or the term starting with B that we use to describe how we define microservices? We need to form a, anyone? Starts with B. Yeah? Brainstorming. Brainstorming, yeah, you'll do some brainstorming. That's not the term. Anyone else? Okay, bounded context. So defining your series of entities, like you would when modeling a domain, we use domain-driven design, and then we form a bounded context, and this will form your composition of your microservices. Okay, cool. Design principles, we talked about that. What's choreography? Anyone? What's it like? It's an analogy for it. It's like a dance. Yes. Thanks, Peter. What about orchestration? In the name. Yep. Anyone? Yeah, it's like a conductor running an orchestra. Cool. Okay, so today, the first thing you should talk about is separating the data model. So I alluded to yesterday this thing of like, okay, well, you know, we've split up all our microservices and we've defined everything. And so here's our account service, here's our content service, here's our enrollment service. But how do we deal with the fact that our database is now distributed across a bunch of different services? And we talked about this thing that shared mutable state is a big problem in software design, where you have all these processes haggling over the same state, and that creates coupling. In parallel programming, that causes concurrency problems. So we have to manage this when we're using microservices. So here we have a bunch of different microservices: product browsing, purchasing, customer account, and product fulfillment. I realize I'm not sharing my screen actually for online people. So let me just quickly jump into Teams. Sorry about that. Here we go. I hope I can do this twice. Let's see how we go. Calendar. Add this device. Cool. Share screen. Here we go. Okay. I hope online people can see that now. So we've got a bunch of different services, and they're all talking to a single database. So these services are all APIs. They're deployed, and then this database is separately deployed as its own entity, and the services talk to the database. Pretty straightforward. That's kind of like what you might have done in your SENG2 project, where you have a bunch of different functions all talking to one database, except here, the functions are their own microservices. Problems with databases, they often don't scale very well. And when I say they don't scale very well, I don't mean like the sorts of applications that you'll necessarily be building, but in industry and in big enterprise pieces of software, when you have, I guess I'll use Jira as an example, when you have hundreds of thousands of issues from these massive, massive companies, you know, with thousands of employees, that's a lot of entries in your database, right? When you go select star from table, or you know, select something from table, you have to go through all the records in that table. That takes a long time. The databases don't scale very well. And then on the other side, we say, okay, let's distribute the database. That often creates complexity. We'll talk in a second about how to manage that complexity. And then another thing about this database is it's a single point of failure. Who, with their security hats on, knows what a single point of failure is? It's not good. Okay. Any more descriptive? Just generally, what's a single point of failure? Yeah, right. Like if you kill the single point of failure, then the whole system goes down, right? It's like you know, like the Death Star, you know, when they put in the things and then the chain reaction causes an explosion. Okay, so separating data model, how can we do it? Because when we go from, as I said before, we start, instead of scaling horizontally, we scale vertically. That means we have to split our database across with it. So the first way to do that is replication, where data is copied across multiple machines. This is the case in database distribution. This is the case in event streaming Apache Kafka. If you're familiar with that, the idea of a partition is literally another machine that the code is running on. Sorry, not the code. It's another machine that your events are being stored on. So replication allows us to scale the database to cope with load. It improves fault tolerance. So if one database goes down, we actually have a copy of it that we can revert to as a backup. And then the third one is to locate databases closer to end users. This isn't a super big consideration for your projects, but if you've done networks, you know the idea of a CDN, right? A content distribution network. Yep. So that is, you know, located closer to someone physically so they can get a faster response. The next way to deal with distributed databases is by partitioning. And by partitioning, I don't mean to split up the tables. I mean literally cut the tables in half. And you know, you've got your enrollments table. Half the records are stored on this machine, and half the records are stored on this machine. That's what we call partitioning. We split the data of a system onto multiple nodes, and they're called partitions. Sorry. And then the third way is independent databases, and this is kind of what we allude to when we talk about bounded context, where each microservice will have its own database. So instead of one massive, huge database that lives in the monolith, each microservice will have all the data that's associated with it, right? That will be its own bounded context. The thing with this third one, though, is that you might get, like we saw before, right? I think it was the customer and the product table split across two different microservices. So you might have copies of the same piece of data across different services. This leads us to, sorry, we'll get to that in a second. We'll talk about eventual consistency and this idea of, you know, you've got two pieces of two services which both are operating on the same piece of data. But before we get to that, who here has done networks on 3331? 1, 2, anyone else? 3. Okay, good chunk of you. Cool. So this isn't like if you've done networks, that's good. If you haven't, that's fine. But it's good to be aware of the fact that you understand the different layers, your application transport network, the different layers of your TCP/IP stack. To understand the fact that when you send bytes across the wire from one microservice to another, you have to deal with stuff, right? You have to deal with the fact that the packet might not reach it. You've moved from a world of, instead of having, here's this Java class calling this other Java class, and it's just a simple method call that all lives within the space of the JVM. We're instead moving to a world where we're sending packets over the wire, and you can't necessarily guarantee that everything's going to succeed. The first problem is reliability, right? And that's the case that we're not sure the network is reliable. There's no guarantees on that front. So one technique that's very commonly used when we're communicating between microservices is using what's called an exponential backoff, which says, okay, I'm going to try to send the packet. Okay, and then I'm going to wait a small amount of time and then try to send the packet again. And you keep trying and trying, and the amount of time you wait becomes longer and longer exponentially, right? Like forming an exponential curve until you've run out of retries and that there's a max retries, which is some constant defined. So this is a useful pattern. Another problem is network latency. Again, you're not calling another Java class anymore. We're having to send bytes across the wire, and that takes time, and that causes latency. Bandwidth isn't infinite. That's all very straightforward because you know that things take time to travel across a network. Then we get to the locked room problem. We'll talk about security in a few slides, but there's no guarantee that the network is secure. So for here, for example, you've got a web page which hosts there's a web application. I think that looks like a backend, and then there's a product browsing microservice. And ideally, your user only interacts with the web page, right? The web page talks to the web server, and the web server talks to the microservice. It's possible for someone to come and pose as the web app, right? Bob, what kind of attack is that called? Does anyone know? Bob comes in and stands in the middle. So we call it man or person in the middle attack, right? So reliability, and that is how often does your software succeed and how often does it fail? When we talk about observability in week 3, one way to measure or to have observability is saying what's the reliability of this particular query or the reliability of this particular endpoint. How many times, what percentage does it succeed and what percentage does it error out? Fault tolerance is saying when your system fails, what steps are in place to recover? Do you have backups? Do you have alternative fallbacks? We'll also talk about this when we get to feature flags, when we can have a fallback feature flag. We'll say if this doesn't work, then we fall back to this old version. Death, taxes, and computer system failure are all inevitable to some degree, which is said by Howard and LeBlanc. Individual computers fail all the time. So when we talk about spreading risk and minimizing risk, we can try and spread the risk of failure over multiple computers. You don't have to worry about this for this course, but this is important background when we're dealing with distributed computing and dealing with microservices. Okay, that's all I had to say on that. All right, this stuff's important, so pay attention because you'll be making these decisions when it comes to designing your microservices. So we have multiple options when it comes to, well, how do we actually interchange data? How do we facilitate communication between our different services? The first way is synchronously, and this you're all pretty familiar with. You send a request, you get a response. That's REST endpoints. That's GraphQL and gRPC. Now we're going to have a separate lecture on GraphQL and gRPC next week because we want you to start using some more advanced and modern technologies because you've all done REST to death at this point, I'm sure. But this general model is, again, request response. It's all synchronous. It's in, when I say real time, like there's some delay, right? As I said before, you're sending packets over the wire, but you're not having to wait some expedited amount of time. The trade-off with this is that there's increased coupling between different services. So here, for example, you've got your UI service that talks to orders, that talks to stock, and there's coupling between those. The other way to do communication is asynchronously. That can still be in the format of request response, and that is what we call a promise if you've done JavaScript, or in Java they're called a future, but it's essentially I'm going to make this request, and at some point in the future, I don't know when, it might be in 5 seconds, it might be in 10 minutes, it might be in 5 hours, you're going to come back to me with the response. And you get this little box, which is a promise that the response will be returned. So you can do data interchange via promises. The other way is via event-driven architecture. If you are interested in this and want to adopt this to your projects, I would recommend checking out a 2511 lecture, which talks about this in a lot of depth about how we, the model of producers and consumers writing to a shared queue. But long story short, instead of having the services talk to one another, there is a buffer or a queue or a channel or a stream, all different terms for the same thing, and producers of events write to the queue and they say, okay, well, this person was added to the system, right? This student was enrolled in this class. And then that event sort of flows down the stream, and then consumers that are interested in that event say, well, I need to know that someone was added to this class so I can update my class list, for example. So you have your, I'll try and write it out. Here's our enrollment service. Here's our queue. And here is our class list. The enrollment service says, okay, Nick was added to the class. That travels down the queue, and then the consumers, and other consumers can do this as well, right? There's no exclusive kind of picking up of events. So this consumer and maybe this consumer B over here as well, and C, if you're interested, they pick up the event, and they can do whatever they like with it. They can store it in the database, they can send some other network requests, they can make more microservice calls, they can do whatever they want. And then you might also have other services like D and E, which aren't interested in this type of event, and they just ignore it. That's a sort of short summary on asynchronous and event-driven communication between services. The way to facilitate that, in 2511 we talked about Apache Kafka, very popular. In AWS you can provision Kafka using MSK, which I think is managed service for Kafka. You can also use Amazon SQS and SNS. They're useful technologies. The good thing about this way is that there's less coupling. You can just add and remove producers and consumers as you like, and you don't have to worry about, well, if I take this producer out, then this consumer that is, waiting for a response like we had up here is gonna error out. You can just have things come and go as you like asynchronously. The main downside is that it's very costly to set up, both in terms of the amount of time and obviously it requires resources for you to maintain this queue as well. We also have the problem in both instances, not just asynchronous, but how do we keep our data model accurate? And again, you've got two microservices that both have information about, let's say, class enrollments. How do you make sure that if one updates, the other updates as well? So the first thing I'll leave you to think about is this thing called the Byzantine generals problem. And it's where n generals agree on a plan, and they can only communicate via messages. They can't actually talk to each other directly. So messages, they can be, this is the sort of age of Julius Caesar, right, when messages can be delayed or lost. And some generals are traitors. So they say, oh, they received the message, but they don't acknowledge that they've received the message. Or people send dishonest messages and pretend to be people that they aren't. So this is in essence the man in the middle problem that we had before. Ways to deal with that: validation, sanitizing your inputs, and where possible, retrieving data from multiple different sources so that you can verify that this message is both correct, has integrity, and it's also from the person who they said it was from. But you don't have to worry about that too much. Probably more important to think about for your projects is these two considerations. The first one of those is idempotency. If you sort a list, right, like I have the numbers. I have numbers 7, 6, 10, 13, and 1. And you sort a list that's going to be, okay, well, 1, 6, 7, 10, 13. And then you sort the list again. Is this going to be any different? No, cool. So idempotency is saying, well, if you sort a list once and then you sort it again, that's the same thing as if you just sorted it once. And you could sort it 1,000,000 times, and that would be the same as if you sorted it once. So we say that sorting is an idempotent operation. What's the problem when your microservice says, okay, well, maybe we've got our enrollments sends an event to the class list service, but then maybe the enrollment service thought that the event didn't send, so it sends it again. So the event Nick enrolled in the class comes to the class list service twice.
They're saying because it's...
What? Oh dear. This is what we're seeing. I thought I shared the screen. Can we please have the screen shared so we can see the slides right? I'm pretty sure the screen is being shared. What we're seeing. I can only see half the slides. That's interesting.
Oh yeah.
Okay. Okay. I'm not sure what's going on, Rowan. Yeah. Yeah, maybe resize your window, just leave the call and come back. Sorry about that. Cool, let's crack on. Where were we? Idempotency. Oh yeah, so we've sent the Nick enrolled in SENG3011. That's been sent twice. What happens the second time when your service receives that event? Does it break? Does it have two records that both say Nick enrolled in the class? So you need to think about how will your service cope with receiving the same thing twice? How will it be idempotent? The next one is eventual consistency, which is saying, well, let's say you have two services and they both contain information on enrollments. What was E1? What was E2? And maybe E2 only reads from enrollments. So they have some enrollments in their database. They both have here. And then E1 updates and sends to E2. But before the update arrives, someone reads from E2 and say, and says, like what's Nick enrolled in? And what we get is what we call a stale read, where someone's reading from E2, but E2 isn't necessarily up to date with all the information that E1 has because the packets are still traveling across the wire. That's the first problem. The second problem is, well, what if these are both right? So let's say, I enrolled in SENG3011, and this service said, actually, I'm going to be enrolled in 2511. And you can only be enrolled in a certain number of courses. So this says, okay, Nick's enrolled in 3 courses. This one says, okay, Nick's enrolled in 3 courses. And then they both send the packets to each other. What's going to happen? Who knows? So you need to think about how your services will deal with these cases. A good way to try and think about it is single sources of truth when it comes to write updates. You don't want all this propagated, you don't want all this separated state between different services that you have to suddenly send to each other and then deal with these write conflicts. So maybe one service is read only and one is write. Again, these are very open problems. These will, how you approach these will depend on your architecture. They will depend on how you've defined your data model and your bounded context. Okay, here's an example that I dealt with the other day about eventual consistency. So we had a bunch of classes and then we changed the timetable several months ago. But the old classes were still appearing in WebCMS. And I think this was just the fact that WebCMS didn't update. And so we had to go and get Jazz to go and manually delete these classes that were sitting there. So again, that's one microservice which is waiting on updates from another microservice that haven't come through yet, and we've gotten a stale read here. Any questions? Cool. Okay, this one's super important, so pay attention. Stateful versus stateless architecture. So everything you've built so far has been what we call stateful, and we've talked about persistence. We've talked about how do you store information in a database, in a text file, in a pickle, whatever. Now we need to think about, well, do we actually want that state in the first place? Maybe we do. And so if we want to have a service which maintains state, which keeps track of some form of record within the service itself, we call that a containerized microservice, and that is providing what we call container as a service. Now, we'll talk about containerization next week and how to do Docker and build Docker images. Very exciting. And if you're building a container service, you'll need to build a container with it, and we'll teach you how to do that. In AWS, containers are provisioned by ECS, or Elastic Container Service, and allows for essentially you to run a container. Like you can think of it as like running your server.py, and it'll just run continuously forever and ever and ever. Now, of course, that costs money, right? Like if your file's just running and running and running, that obviously takes resources on AWS, and that's more expensive than if you just had a piece of code that's pay as you go. You say, call this function and then that's it, because this is continually running in a container. So it's more expensive, but it allows for persistence. So you can make a request and then you can make a second request and rely on the state of the first request being saved, like any stateful application. It's really useful for heavy and continuous computation. So if you were processing a data stream and it would take maybe several hours or days to get through that data stream, you want things to be running constantly, right? So that you're always active. And you get more control over the running environment of the business logic. So that's stateful. The second type is stateless architecture. And we do that by building Lambda microservices. Now, who knows what a Lambda is? In Python, in Java? Anyone? Yeah, sorry. Lambda?
Like a constant function that's not associated with like state or class or object. Independent.
Yeah, well put. It's an anonymous function that's not necessarily associated with any particular other process, and it's often stateless, right? Like you don't, and I think in Java it's the case where you can't actually mutate local variables in a Lambda. It doesn't matter. The point of it, a Lambda in AWS is the same idea, where it's like a toaster, right? Like you call it, there's local variables within it, and then local variables die and get garbage collected, so to speak, when the Lambda finishes. So we call this function as a service, and provision using Lambdas, and they have things that take input and they produce output. Now that's not to say that Lambdas can't modify state, because what you can have, which I think is on the next slide, yeah, and what you can have is a Lambda that updates another microservice, and that is stateful. So a Lambda might update a database or an Elasticsearch instance, for example. So your element itself doesn't have to be stateful, but it might work with something that is stateful, like a cache or database. Now, if you want to say, okay, I'm going to build a bunch of different Lambdas that are all part of the same microservice, you can group them using what's called an API gateway. Again, you can provision this in AWS. And what's really useful is that if you invoke the same endpoint concurrently, it's all independent, right? Because there's no state. We don't have to deal with concurrency problems. And it's only active when the function is called. So whenever you call that function, that's when you pay for it in AWS. So if you call it once, you get paid, you get charged like 1 cent. If you call it 10 times, 100 times, you get paid you get charged accordingly, as opposed to a container, which is just continually running and raking up the credit bill. It's useful when the workload is small and the operation takes a few seconds. And the emphasis is on the business logic itself, the quick operations that don't take very much time. Webster, who is the guy who's been awesome in setting up a lot of this environment that you'll be working with over the next few weeks, he reckons that most of you will be building most of you should be building Lambda microservices because you won't need a whole lot of state. That's not to say you can't or shouldn't build a containerized service. The main thing from our end is that you don't spend too much money, and we'll kind of help you out with that and provide some things to make sure that we know how much you're spending and you know how much you're spending as well. Okay, and again, here's an example. So you have just some front ends that are interacting with an API, and the API consists of a series of Lambda endpoints which interact with the database. So again, stateless Lambdas, but they interact with stateful components. Okay, here's some examples. I'll give you like a minute or maybe 2 minutes. Turn to the person next to you and think about whether each of these would be stateful or stateless, whether you want to go with containerized or Lambda microservices for this approach. Questions? All right, go. You have until 12:35.
Generating and validating. Yeah. Yes. Or you have stateful authentication. Like, I guess it's what part of like you need to keep track of mine and like yeah, and also
Okay, got another 30 seconds. Just try and get the first 3 again.
yeah.
Okay, cool. Let's call it there. All right, first one. Put your hand up if you think stateful. Put your hand up if you think stateless. Cool. The thing about the database is that it's deployed separately in the ecosystem. So what we can get is essentially what we have here, where you would go for stateless because you don't actually need to store the state in the microservice itself, right? Like if you were saying we're going to have the database within the microservice that's directly interacting with your API, you'd want stateful. Oops, sorry. Okay, next one, generating and validating JWTs, JSON Web Tokens. I think we actually have this in our system. Who reckons stateful? Put your hand up. Put your hand up and feel unrestrained and completely ignore what everyone else is saying, if you think this is the answer. Who reckons stateless? Okay, most people. Yeah, the stateless is right. You don't necessarily need to keep track of JWTs, and even if you did, you might use a separate cache for that. So it's a simple, again, it's a business operation. You're managing an auth token. All right, instant messaging service. Who reckons stateful? Who reckons stateless? Okay, anyone have any arguments for or against? Yeah.
Like, keep track of who's received messages. That alone state.
Mm-hmm.
I'm sure there's a lot of stuff that could be stateless, like, but just that alone, I think.
Yeah, I would say stateful, because you want to keep track of who's sent messages, who's received messages, and have it continuously running in a loop. Cool. Fetch and process the weather every 1 minute. Stateful or stateless? Who reckons stateful? Who reckons stateless? Probably stateful. Like stateless will probably work here. You can have these things called scheduled lambdas, which run at a certain interval. I've kind of given away the next one, but fetch and process the weather every 12 hours. Who reckons stateful? Who reckons stateless? I'll probably say stateless here, because you only need to run it once every 12 hours, and then you have 11 hours and 59 minutes. It's like a lot of money. Okay, this last one, you can probably break down into a series of different components. So we run machine learning on a data stream, we store the results, and then we use the results to make predictions. So the first part, running machine learning on a data stream, who reckons stateful? Who reckons stateless? For those of you who know anything about machine learning, what do we know about it? Is it computationally intensive? Yes, very computationally intensive. So it'll take a while. It might take 5 hours for you to run this machine learning model. So we want stateful for that, so we can continuously run it in a container. Then we store the results. But what about making predictions? Will we use stateful or stateless for that? Yeah, I reckon stateless, because you're just saying, what's the prediction? That's a simple, quick operation. Yeah.
Is there any reason you're going stateful on the machine learning? You say to process all the data, but can't you do that with the stateless thing? Like if it receives input, process it for 5 hours or so, send it along to a different microservice, and then close, right? Like. Yeah.
You could do that. Lambdas are better for short operations that take a short amount of time. So that's why. Okay. All right, security, important. When we talked about the UNSW ecosystem yesterday, one of the big things in any software ecosystem is how do you keep everything secure, and how do you not have 50 million different passwords for all these applications that we're using? And we solved that using SSO, all right, single sign-on. In a microservice context, we can have a microservice which has a whole job just for managing authentication. And I'm pretty sure when you start working with our microservice ecosystem, you'll be interacting with a service that just manages JWTs and handles all the auth instead of you having to do that yourselves. Another thing we need to think about is, okay, what kind of traffic are we getting? What kind of communications do we have to deal with? And if we go back to what we were talking about before with networks, we deal with the locked room problem, right? For those of you who've done security, any microservice is just this sort of person sitting in a room and they're being fed notes, but they don't know where the notes are from or who they're communicating with, and so that could be some intruder, right? Some person in the middle. So we need to consider what's called north-south traffic, which is traffic coming from external clients or customers, right? Anyone calling your API from the outside. And we also need to consider east to west traffic, which is communication between microservices. So we handle authentication and authorization. And a way to deal with north-south traffic is centralizing points of entry into the ecosystem. So a very common pattern is all your whole ecosystem is, instead of having like what you had in SENG2, where everything is deployed as its own public API, literally anyone on the internet can come and query any of those APIs. We don't have that. All of your services are deployed in a private network. So here's the ecosystem. Here's service 1, service 2, service 3. So when, going back to the biology example, it's kind of like a membrane and all your organelles floating around. And then you have one service, which is what's called an edge service. And that handles all of the public-facing requests. this is also really useful because when you're doing, like, let's say you have a front end, which is like a mobile app or a website or whatever, instead of the front end making like 50 billion different calls to the microservice system to do the orchestration, you have one service which it talks to, which is the edge service, and that can do choreography, that can do orchestration. But the point is that's the single point of entry into the system, and that does facilitates communication. These internal services make their own calls to one another, but everything ultimately comes through this edge service. And that's very, very common. It's also common that that service is written in GraphQL. So that's a bit on north-south traffic. And again, we can see here, user talks to web client, and the web client talks to a server that's managed with some sort of authentication. And then those front-facing APIs talk to the internals of the microservice system. And there's usually some form of identity provider as well, which is either our SSO or our auth service, if we've implemented it ourselves. The next one is east-west traffic. Does everyone know what TLS is, or Transport Layer Security? Does anyone not know what TLS is? Perfectly fine. Roughly, if you do either networks or security, you'll probably cover it. It's essentially just encryption that happens at the transport layer. So when you're sending your packets, just before you get to sending them over the wire, there's some encryption. So that means that only service A and service C can understand what they're saying to each other because they have some sort of shared key or some sort of private shared key. Any questions on security stuff? Awesome. Okay, we're about to wrap up. So overall, as I said, all software architecture is trade-offs. When it comes to monolith versus microservice, at the moment anyway, this might change in 5 years. I think that people I talk to say that the pendulum has kind of swung too far one way, in the sense that we've kind of got to building nano services. Like there's too many microservices and there's too much glue to manage. And we've just talked about all this different glue and how do we deal with services talking to one another. But there's lots of benefits as well. So you can choose your tech stack. And this is another really useful benefit. Like you can say, I'm going to build this API in Python. I'm going to build this API in Java. I'll build this one in C++, as opposed to let's build this massive monolith in Java or something. Less responsibility, less coupling. We talked about that. It's easier to test, faster build and release cycles. Again, you don't have this big monolith which takes an hour for the CI to run. And there's lower risk per microservice. And we sort of keep talking about this idea of risk. Hayden Smith is going to come and next week talk about risk management and the principles of risk management, and you'll see that a lot in this course as to how do we design our software and how do we design our processes to minimize risk, which is things going wrong. Not a single point of failure and easier to scale. All right. There's also cost as well, which we've talked about. Either everything breaks or the glue breaks. And so from a business point of view, and I've worked at places where I worked at one place where the CTO went, we've thought about microservices, but it's just too much of a trade-off where maybe, all that time that you would have saved waiting for your CI to run, because now you've got a shorter build time, we spend that time instead dealing with all this glue, dealing with communication between services and things breaking. So again, that's a trade-off. A lot of businesses are tending towards microservices and have made that decision. You have to deal with distributed systems. We talked about that. There's overhead, there's complexity. Again, there's risk as well. There's risk no matter which way you go. There's more complex deployment, security, and debugging is hard as well. So when we talk about observability, we'll talk about distributed tracing, which is saying, how do you trace, maybe a request comes in, it's the edge service, and goes to 1, 2, 3. How do you follow that request across all the different services? Great, I said everything there. These are all the references. Are there any questions on the microservice ecosystem? Yeah, what's your name?
How do you decide what size of your microservice? Like, you get more experience this time with it, but you just touch on getting too small of a microservice.
Yep.
But presumably, if you create something that's too large, you're essentially just barely splitting it up into random nodes that have a state and faster and cheaper.
Yeah, and if you don't make your microservices small enough, you end up with essentially a series of distributed monoliths. Then you have monoliths, and then you also have to deal with glue, so you kind of get the worst of both worlds. There's no hard and fast rule, and I couldn't tell you, to be honest. But for you and your projects, because you'll be working on an individual microservice and might have to sort of communicate across teams to figure out which, who's going to do what functionality. I don't think it'll be, you won't have to see like the hard parts of that, but certainly like if you go into industry, I would be very surprised if you didn't come across either services which are like, they're so small, what are they doing? They're these little nano services and there's like 100 of them, or the opposite where you say, well, this is basically just another monolith.
What to do with managing around the capabilities of the product. Yesterday, the speaker from Optibus said they organize one microservice per person, 1 person. It's a good question. Trade-offs vary. It started as a microservice, halfway through you realize quite big, or vice versa, ends up being too small.
Yep. Cool, thanks everyone. You got your bit now?
Yeah, I'll
I got another question.
Yeah, sure.
Are there any articles or slides on how to deploy and work with microservice? Because in the past we've worked with kind of like a single service and a server.
Yeah.
Kind of things like, do you have different Git repos, or do you have like one Git repo with different parts that CI into the services? Those kind of questions.
Yeah, it's very sort of, you just figure out what to do and it's up to you. Like there's heaps of documentation online though, and you can see how different companies and people have done it.
Each company will have its own setting. For us, that's the difficulty, is we chose a certain setting. And next week, you're going to be having information about the setting that we've done. It's not necessarily the best setting. So you'll have to learn how to use it. We also want you to get the opportunity to make comments. Oh yeah, why are you doing it this way? So again, we are simulating being a company where we do it in a certain way. As people will come up with other ideas. But that's one of the difficulties in this space. There's so many options. There's so many vendors trying to push their own agenda. To find the right setting. So Nick said everything there is to say about microservices. So I'm here just to kind of quickly summarize at a high level some of the things that were mentioned by focusing on the architecture at the highest possible level. So the software architecture is a piece of design. You have to remember the microservice architecture is an architecture is design. So ultimately, this is all part of software design. And I think that's something that many people forget. So designing complex architecture is difficult, and you find a way to break it into pieces. And then the service-oriented computing paradigm came and say, you have to break everything as a service and build web services. Now, the concept of web service is to have a component that have a web interface, and you can query it and get a piece of functionality. But then within that, there were so many different options. And these options on how to design the software architecture cause problems, because in the old days, you do software design and then you do the implementation. But with Agile, you're doing bits of the implementation according to different user stories. So that actually creates a conflict, because on the one hand, you have to have the architecture done before you do the coding. On the other hand, we're saying you have to do the coding before you have the architecture. I always found that somehow the concept of agile methods and architectures on the surface don't seem to work together. However, you have to learn on how to do your design as you do in your implementation, as you do in agile methods. And that's not something that gets taught. We are taught agile methods. You build your stories, but we are not taught about, how is this building of the software is going to affect your architecture. Because if your architecture keeps changing, it's a problem. Because everybody is following the same architecture. As I'm building it, I'm changing it, it affects everybody else. So that's a hard problem. And I just picked an architecture. So we have an architecture, and in this architecture, different people are working on different components. And as they work on components, there may be changes that affect each other. How can you manage that? So one strategy is always to have stories that operate on slices. So story one will be a little bit of the query builder, a little bit of the query processor, and few tables from the corporate. So when you do story one, you have an initial architecture with 3 components. Then the second story will build you different components to make the second story, and the 2 stories are using different components. They are not linked yet. And then the third story will use some of the components that you've built from the second story, and so on. So it's important to be aware that agile methods, if you're not careful, can result in a messy architecture. But if you're careful, you have an architecture and you somehow relate the stories that you are building in agile according to the architecture, and you're building the architecture components in an incremental way, then that solves the problem. And microservices, they facilitate that, because you can build your stories according to separate microservices. And when it comes to putting them together, it's much easier than if you don't have a microservice architecture. Nick mentioned the Conway principle, and this is where microservices concept differs from the traditional web service. A web service, it's an API, it's a technical API, and it's basically an extension of a software component. But microservices are really built around the business domain, and Nick was explained very well this bounded context, and that's very important, that we are not looking at technical component that we are putting on the with web interface, but these components represent business functions. So one of the things in the naming of the microservices, if we have some cryptic name, then that's not a good microservice. So microservice has to be managed order, managed. I think yesterday we mentioned Web CMS being developed as a microservice. So all the microservices have to be, for example, manage this particular course, or manage users, or manage. So they have to have some meaningful names that a business person will understand. So the main characteristics, again, Nick mentioned, is that you don't have, you have a distributed architecture, separately deployed, the bounded context, share nothing, and different services have their different databases. So essentially, that solves the problem of the previous architectural paradigm, which was the 3-tier architecture, where you had a database that contained all the information. And the reason why the microservice came is because maintaining a global model was very hard. It was much easier to split the data model across multiple microservices. So this is what Nick was talking about in the bounded context. And then API layer would be what the user would see, and different components will be accessible in a uniform way. So a microservice setting within a company has to sort these questions of accessibility, deployment, security, and so on. And that's something we try to do within this course. But the way we do it doesn't have to be right or wrong. It's one way. And I think for you, it's more to be aware of the issues, the difficulties, and also having to comply with some kind of organizational, a set of organization policies. So the advantages, just to summarize what's been said, it has that incremental development, and it works well with agile methods. As I explained, agile methods, if you're not using a good architecture, it could break your system. It could lead to a chaotic design, whereas agile and microservices work well together. Plus, the microservices are well supported by DevOps technologies. And we're going to mention a little bit about DevOps at the end. Okay, so I think that's just to conclude the part of the microservice architectures. I don't know, do we want to have a break then talk about the sprint one? Okay, so we're going to have a short break. And then in the second part of the lecture, we're going to talk about sprint one requirements. And then I'll mention a few things on DevOps, and that will be followed by a lecture on theory of constraints by Nick. Okay, so we'll resume in 10 minutes. Yeah.